here we're going to be talking about how to take the derivative and the integral of exponential functions, specifically those that have a base of e. So this is going to be our main rule, or really our only rule, for differentiating exponential functions. The derivative of e to the u is equal to u prime multiplied by e to the u. So let's start off with example 1. Our function f of x is equal to e raised to the negative 6x. I'm going to rewrite that exponent as e to the negative 6, x to the negative 1. So I'm just bringing the x up from the denominator and writing it in the numerator with an exponent of negative 1. That's going to help us when we go to take our u prime. U is everything in the exponent of e. So for our case in example 1, u is equal to negative 6x to the negative 1. We're going to take u prime using the power rule. So I'm going to bring down the exponent of negative 1 and multiply it with the negative 6 to get a positive 6. And the new exponent on x will decrease by 1 to become negative 2. So now that we have u and u prime, we'll be plugging those in to this right here, what I just boxed in blue, to get that our f prime of x is equal to u prime, which is 6x to the negative 2, multiplied by e to the u, which is e raised to the negative 6x to the negative 1. The last thing I'm going to do is just rewrite this so we don't have so many negative exponents. I will rewrite the x to the negative 2 as an x to the positive 2 in the denominator, and our new exponent on e will be negative 6 divided by x to give us our final answer for our derivative of this function. In example 2, our function is a quotient, so we will need to use the quotient rule. I'm going to start off by identifying f and g. F is always what's in the numerator, which is e to the y squared, and g is what's in the denominator, which is e to the y minus 5. Now remember that in this problem here, y is our independent variable. So in this problem, the derivative of y is 1. I'm going to go in and identify u for each of these two functions. So for f, remember that u is everything that is in the exponent of e. U is everything that is in the exponent of e. So for f, our u is y squared, and our u prime is 2y. So our f prime, to get f prime, we're filling out u prime e to the u. That's how we take the derivative of exponential functions. So our f prime is 2y e to the y squared. I'm also going to go and identify u for the function g. U is everything that's in the exponent of e, so in this case u is y. U prime is simply 1. The derivative of y is 1. Y is our independent variable here. So our g prime, again, we're filling out u prime e to the u. U prime is 1, and then e to the u is just e to the y. So our g prime is just e to the y. So now that we have all 4 of those, we're ready to go and write what our derivative for our function is, our h prime of y. Remember that we are using the quotient rule, which is f prime g minus g prime f all over g squared. So for f prime, we have 2y e to the y squared, and then we're multiplying. Make sure that this looks like this is an exponent on the e. And then we're multiplying that by g, which is e to the y minus 5. And then from that, we are subtracting g prime, which is just e to the y, and that's multiplied by f, which is e to the y squared. And then all of this is divided by g squared, which is e to the y minus 5 all squared. And this is our derivative for example 2. Example 3, we have this function s of t. We will need to use the chain rule in order to take this derivative, or the general power rule, which is an application of the chain rule. So I'm going to start off taking s prime of t by bringing that exponent of 5 down in front of the function. We keep everything that's on the inside of the function the same. That new exponent drops by 1 to give us a new exponent of 4. And then the chain rule says that on the outside, we have to multiply by the derivative of everything that was on the inside of the function. The derivative of e to the negative 7t plus e to the 8t. So I'm going to go ahead and bring down my 5. I'll bring down everything we had in the front. And then I'm going to go ahead and take this derivative of what's on the inside here. For the e to the negative 7t term, our u is negative 7t, and our u prime is negative 7. So that derivative is u prime e to the u. Then we will be adding the derivative of the e to the 8t. For that case, our u is 8t, and our u prime is 8. So this derivative is u prime e to the u. And then I'll close my parentheses, and that will give us our answer for this derivative. Example 4, we want to find any points of relative extrema using the second derivative test. We have to start off by taking the first derivative, and to take the first derivative, we will need to use the product rule because we do have a product here in our function y. I will let f be 3x, and I will let g be e to the 4 minus x. Our f prime, the derivative of 3x, is just 3. And for g prime, to take this derivative, we will be using the same rule we have at the top of this note sheet. Our u is 4 minus x. That's everything that's in the exponent of e. And our u prime is a negative 1. So g prime, this derivative is u prime, which is negative 1, e to the u. So that is e to the 4 minus x. And that is negative in the front because of the u prime. We are using the product rule here. So our y prime, our first derivative, is f prime g plus g prime f, but g prime is negative, so it will be minus 3x e to the 4 minus x. So now that we have our first derivative, we're going to go and find our critical points, which is places where the first derivative either does not exist or places where the first derivative is equal to 0. The first derivative is a combination of a linear term, that x we see right here, and exponentials. That's always going to exist. The domain of that function is all real numbers, so there are no places where the first derivative does not exist. I'm going to go ahead and set the first derivative equal to 0 to find any critical values that we may have. We're going to solve this equation by factoring. We can factor out a 3e to the 4 minus x, which is going to leave us with a 1 minus x on the inside of the parentheses, and then I'll go and I'll set both of these factors equal to 0. If you remember, exponential functions, unless they have been shifted down, they never equal 0. So this is never going to happen. So we won't get any critical values from that first factor, but 1 minus x will equal 0 when x is equal to 1. So we only have one critical value, and it is 1. Now we need to go and take our second derivative, and then we will plug 1, our critical value, into our second derivative to see whether we get out a positive number, which tells us that we have a local minimum, or to see whether we get out a negative number that tells us that we have a local maximum. So I'm just going to rewrite the first derivative up here. I'm also going to go ahead and set up a product rule because we will, actually, no, we won't. Let's go ahead and start taking this derivative to get y double prime. So for the derivative, I'm going to leave some more space in here, y double prime. For the derivative of the first term, this 3e to the 4 minus x, we know that the constant of 3 will stay in front. To take the derivative of e to the 4 minus x, our u will be 4 minus x, everything that's in the exponent of e, and our u prime will be negative 1. So that derivative will be negative u prime, will be u prime e to the u. So u prime is going to give us a negative in the front, and then the e to the u will just be e raised to the 4 minus x. For that second derivative, what I had started to say earlier is that we're going to need to use a product rule to take this derivative here, which typically we would, but if you notice, what I underlined in green is the exact same thing as the original function, and we've already taken that derivative, and we got y prime. Now be careful here because there is a minus sign that does need to be brought down, and then in parentheses I will write what the derivative of what I underlined in green is. And remember that that derivative is simply our y prime. Now I'm going to go ahead and plug in 1 because, well, first I'll distribute the negative just to make this a little bit cleaner. And combine some like terms. Make sure you turn that last term into a plus because the negative has to go to the first term and also to the second term. I'm going to go ahead and combine the first two because those are like terms to give us a negative 6e to the 4 minus x plus 3x e to the 4 minus x. And now I'm going to see what y double prime of 1 is. So this is negative 6e to the 3 plus 3e to the 3. Now this is equal to negative 3e to the 3, which is less than 0. And so because that is less than 0, that tells us we have a local maximum at x is equal to 1. Oh, I'll leave some space there. A local max of something. And we know that it is at our critical value of x is equal to 1. And to figure out what the local maximum is, we will be plugging 1 into the original function to see what the function value at 1 is. So I'm looking back up here at the original function to give me 3 times 1 e to the 4 minus 1, which gives me a local maximum of 3e to the 3. Example 5, we're finding the equation of a tangent line to f of x at a certain given value. So our answer is going to be the equation of a line y minus y1 is equal to m times x minus x1. I'm going to go ahead and box this in right here because whatever we fill in here will be our answer. Y minus, we'll have to go and find y1, so I'll leave that blank for now. We'll also have to go and find m, so I'll leave that blank for now. But the x1 was already given to us as 2. We can go ahead and find y1 by plugging in 2 into the original function, f of 2. So we have e to the negative 2 times 2 plus 2 squared, which is e to the negative 4 plus 4, which is e to the 0, which is 1. So we have y minus 1 equals. Now we will have to go and find our m, and our m is going to be equal to f prime of 2. We'll have to take the derivative of that function and then plug in 2. So let's get started taking the derivative of this function. U is going to be everything that is in the exponent, negative 2x plus x squared. U prime is going to be negative 2 plus 2x. And so now that we know that, we can write our f prime of x using the rule u prime e to the u. So u prime, we have negative 2 plus 2x. All that's multiplied by e to the u, which is e to the negative 2x plus x squared. And then to get our m value, we are going to be plugging 2 into this derivative. So we have negative 2 plus 2 times 2 multiplied by e to the negative 2 times 2 plus 2 squared. So we have negative 2 plus 4. I'll go ahead and write that. Negative 2 plus 4 e to the 0. E to the 0 is just 1, and so all of this is just equal to a positive 2 because we have 2 times 1. So I'll fill in a 2 there for our slope, and that gives us our answer for the equation of that tangent line. In example 6, you will be finding any points of inflection and discussing concavity. So to find possible points of inflection and to discuss concavity, we need to find the second derivative. We'll start by finding the first derivative, and to find the first derivative, we will need to use the product rule because we do have 2 separate things multiplied together. F is 2 minus x, and so our f prime is simply negative 1. Our g is e to the x, and so our g prime is also e to the x. Remember, the rule we use is u prime e to the u, and in this case u is x and u prime is 1. So that is u prime e to the u. 1 multiplied by e to the x is just e to the x. So now that we have all 4 of those pieces, we can write our first derivative, f prime of x. So we have f prime g which is negative 1 times e to the x, so that's a negative e to the x, multiplied by g prime f, and so we are, or added to the product of g prime f, so we are adding 2 minus x multiplied by e to the x. So we have our first derivative. Now let's go in and take our second derivative, f double prime of x. The derivative of negative e to the x is simply negative e to the x. The negative just comes down as a coefficient of negative 1, a constant that you can pull out, and the derivative of e to the x is just e to the x. We talked about that up here. We see the same theme that we saw a couple of examples ago, where now we need to be taking the derivative of this second term of the first derivative that I underlined in green. But that second term of the first derivative is exactly the original function. And we've already taken that derivative. And we got f prime. So I'm just going to copy over f prime. So I erase that plus sign because the derivative of what's underlined in green is everything that I just circled here. We saw that when we did the product rule. So I'm going to write a negative e to the x plus 2 minus x multiplied by e to the x. I'm going to go ahead and combine some like terms and simplify this, since we will be needing to set this equation equal to 0. Combining the first two terms gives us a negative 2 e to the x. I'm going to distribute over here to give me a 2 e to the x minus x e to the x. The first two terms will cancel and just leave us with a second derivative equal to negative x e to the x. To find possible points of inflection, we will set our second derivative equal to 0. So we have 0 equals negative x e to the x. I'll set both of those factors equal to 0, the negative x and the e to the x. E to the x never equals 0, but we do get one possible point of inflection at x is equal to 0. So now I am going to create a number line, and this is a number line for the second derivative. I will put 0 on the number line, and we will need to choose two test values, one to the left of 0 and one to the right of 0. I'm just going to test negative 1 and 1, and we're plugging both of these into the second derivative. F double prime of negative 1, plugging negative 1 into the second derivative, and our second derivative is right up there, is going to be a negative 1 e to the negative 1, which does come out to be a positive number because this is simply 1 over e, and that is greater than 0. Then I will be plugging 1 into our second derivative, f double prime of 1. So I'm still plugging in to the second derivative here to give me a negative 1 e to the 1, which does come out to be a negative number because that is simply negative e. And so because we do have that change in sign from positive to negative, we do have a point of inflection with an x coordinate of 0. To get the y coordinate, we would need to plug 0 into the original function here. So we have 2 minus 0 e to the 0, which just gives us 2, because that is 2 times 1. And we can see that the function is concave up on the interval that we got the plus, which was from negative infinity to 0. And the graph is concave down on the interval that we got the minus in our number line, which was 0 to infinity. So all of the examples that we have looked at so far were either of taking the derivative of an exponential function or using an application of the derivative or derivatives of exponential functions. Now we're going to move on to integrating and applications of the integral of an exponential function. So we have our integration rule here, that the integral of e to the u du is equal to e to the u plus c. So looking at example 7, we will need to use u substitution in order to evaluate this integral. Remember, we want to pick u so that the derivative of u shows up somewhere else in the integral. I'm going to take a few seconds to just rewrite this function to help you see how our substitution is going to work. I'm going to rewrite this as e to the 1 over x multiplied by 1 over x squared dx. And then if you still don't yet see exactly what we're going to be doing, I'm going to take this one step further, and write this as e to the x to the negative 1 multiplied by x to the negative 2 dx. So I have not changed anything yet. I have not integrated anything yet. I have just rewritten the function to make our substitution go a little bit more smoothly. And again, if you're still struggling with choosing what u is, the integration formula kind of gives it to us. U needs to be what's in the exponent of e. So our u is going to be x to the negative 1. Now I am going to go in and take Now I'm going to go in and take du, because we are integrating here, so we don't need u prime, we need du, which is the derivative of u, which will be negative x to the negative 2 dx. We don't have that negative in front of our x to the negative 2 dx in our integral, so I'm going to multiply both sides of this equation by a negative 1 to get that negative du is equal to x to the negative 2 dx. So now I'm ready to come in and do my substitution. We have the integral. The e to the u is that first part of the integral. U is what's circled in red. And then what's underlined in blue, the x to the negative 2 dx, that is negative du. So I'll stick a negative out in front of my integral, and I'll stick a du at the end. I'm just bringing the negative down. All of this green box, this e to the u du inside the integral, is everything we have here. And that formula tells us that that is equal to e to the u plus c. And then the last thing that I will do is just go back in and substitute in what u is. And u was x to the negative 1, which is just 1 over x. So we have a negative e to the 1 over x plus c. Example 8, we will be Example 8, it will be evaluating this definite integral. I am again going to choose u to be everything that is in the exponent of e. So u is equal to a negative x squared. We will then come in and take our du to give us a negative 2x dx. We do not have the negative 2, but we do have the x dx. So I'm going to divide both sides of this equation by a negative 2, or multiply both sides of this equation by a negative 1/2 to get that negative 1/2 du is equal to x dx. So now we're almost ready to go ahead and set up our integral. I am not writing any limits on our integral because we will need to change them. What's circled in red is on the exponent of e, so that will be our e to the u. And then what's underlined in blue is a negative 1/2 du, so I have a negative 1/2 in front of the integral and a du at the end. I'm going to come down here and make a little table to get my new limits for my integral, using the fact that u is equal to negative x squared. We have old limits of 0 and 1. We will be plugging those into u. When we plug 0 into u, we still get out 0, so our lower limit stays 0. And when we plug 1 into u, we now get out a negative 1, so our new upper limit is a negative 1. It is important that you keep the order of the limits the same. So if 1 was our old upper limit, then what we got when we plugged in 1, which was negative 1, needs to be our new upper limit. I'm going to go ahead and bring down this coefficient of negative 1/2 in front of the integral. The integral of e to the u is e to the u, and then we will evaluate that from 0 to negative 1. The fundamental theorem of calculus tells us that we do need to plug in our upper limit first, and then we subtract and plug in our lower limit of 0. So we have a negative 1/2 multiplied by e to the negative 1 is just 1 over e, and e to the 0 is 1. And there is our answer. If you wanted to distribute that negative 1/2, you could, to get a negative 1 over 2e plus 1/2. Either one of these answers would be perfectly fine. Example 9, we're going to start off the same way we did in example 8. We let u be everything that is in the exponent of e. So our u is equal to sine of pi theta. Then we will come in and take du, the derivative of sine pi theta. We will have to use the chain rule here. The derivative of cosine, The derivative of sine is cosine. So we have cosine pi theta. But the chain rule says we have to multiply by the derivative of pi theta, which is pi. and we do get our d theta at the end. But we do not have that pi in our integral, so I'm going to divide both sides of this equation by pi to get that 1 over pi du is equal to cosine pi theta d theta. And now we're almost ready to start setting up our new integral. We will have to come in and find some new limits. But we do have the integral of e to the u, and then this cosine pi theta d theta is 1 over pi du. Now I will come down here and find some new limits to see, well, what is u, which was sine pi theta, when x is 0 and, when theta is 0 and pi over 2. When theta is 0, plugging 0 into u, sine of pi times 0 is sine of 0, which is just 0. And then plugging pi over 2 into that will give us sine of pi times pi over 2, which will be sine of pi squared over 2. So our new lower limit, well, our lower limit stays 0, but our new upper limit is sine of pi squared divided by 2. So now we're ready to integrate. I'll bring down that coefficient constant of 1 over pi. The integral of e to the u is e to the u, and we will evaluate that from 0 to sine of pi squared over 2. I'll keep the 1 over pi out in front. Fundamental theorem of calculus tells us to plug in our upper limit first. So we have e to the sine of pi squared over 2, and then we are subtracting e to the 0, and e to the 0 is simply 1. Example 10, we want to solve this differential equation. We're going to start off by integrating the second derivative in order to give us the first derivative. So I'm going to be taking the integral of f double prime. So I'm going to be taking the integral of 1/2 e to the x plus e to the negative x dx. I'll go ahead and pull out that constant of 1/2 out in front of my integral. So I have 1/2 the integral of e to the x plus e to the negative x dx. The integral of e to the x is simply e to the x. And then for the integral of e to the, well, let's talk about that real quick. The integral of e to the x dx. The rule says the integral of e to the u du is e to the u plus c. So in this case, u is x and du is dx. So we do just have the integral of e to the u du, which is e to the u plus c. And our u was x. So we do just get e to the x plus c. And I'll add the c on later at the end. Go ahead and open up some parentheses here. Let's look at the integral of e to the negative x dx. In this case, u is negative x, and so du is negative dx. But we don't have that negative in the integral, so I'll multiply both sides of this equation to get that negative du is dx. So when we came over here to do this substitution, we would have the integral of e to the u, but dx would be getting replaced by a negative du. So then that would leave us with negative e to the u plus c, and then u is negative x, so that is negative e to the negative x. So the integral of e to the negative x is negative e to the negative x. And I do have my plus c here. So this is our f prime. I'm going to go ahead and use our first initial condition that f prime of 0 is 0. So f prime of 0 is 1/2. Remember that anything raised to the 0 power is 1. So e to the 0 is 1 minus e to the 0 is 1 plus c. So we do get that, and all of this is equal to 0. So we do get that 1/2, these cancel, c is equal to 0, which tells us that c is equal to 0. So we do now know that f prime of x, the first derivative, is 1/2 e to the x minus e to the negative x. So I put in this value for c right there. Remember, all of this was f prime. So now that we have our first derivative, I'm now going to integrate that again to give us our original function. So the integral of f prime of x dx is the integral of 1/2 e to the x minus e to the negative x dx. I'll just go ahead and pull that constant of 1/2 out in front. We've already integrated both of these terms, but we'll do it again. So we have 1/2 multiplied by the integral of e to the x is e to the x. Bring down that minus that was already there. The integral of e to the negative x is negative e to the negative x. And then I will add c on the inside of those parentheses. So I do have here 1/2 e to the x plus e to the negative x plus c. And this is for our original function f of x. And we do have the condition that f of 0 is equal to 0. And we will use that to find our c value. Remember that anything with an exponent of 0 on it is equal to 1. So I do have that 1/2 times 2 plus c is equal to e. We're trying to solve for c here. I'll go ahead and multiply both sides of this equation by 2. I'll write this up here to get rid of that 1/2. So times 2, I get that 2 plus c is equal to 2e, and then I will subtract 2 from both sides to see that c is equal to 2e minus 2 to get that our f, our final answer, is equal to, we're going to be putting our c value back in here, 1/2 e to the x plus e to the negative x plus 2e minus 2. And that is our answer there. Our last example, we will be looking at another application of the integral. We will be using the integral to find the area of the region bounded by some curves. So I'm going to go ahead and set up my definite integral. My lower limit will be 0. My upper limit will be the square root of 6. And I will be integrating the function y, which is x e to the negative x squared divided by 4 dx. The y being equal to 0, that just means that we're integrating this function above the x-axis. We're just finding the area under this curve and above the x-axis. So we already have our definite integral set up. I'm going to let u be everything that is in the exponent. So u is equal to negative x squared over 4. You may find it easier to write this as a negative 1/4 x squared. I'll go ahead and take du using the power rule. I'll bring down the exponent of 2 to give me a negative 2 over 4, which is a negative 1/2. The new exponent on x is just 1, and we do pick up a dx. Now we do have an x dx showing up in our integral, but we do not have that negative 1/2. And so I'm going to go ahead and multiply both sides of this equation by negative 2 to give me that negative 2 du is equal to x dx. I'm also going to go ahead and find our new limits of integration because we did use substitution here. I'm going to use the fact that u is negative 1/4 x squared to see what u is when x is 0 and when x is the square root of 6. So when I plug 0 into u, I just get out 0. When I plug the square root of 6 into u, we get 1/4 multiplied by the square root of 6 squared. Square root of 6 squared is just 6. So this is a negative 6 over 4, which is a negative 3 over 2. So now that we have our new limits, we know that our integral can be rewritten with a new lower limit of 0 and a new upper limit of negative 3/2. We do have e to the u, but the x dx is being replaced by a negative 2 du. So now let's integrate. I'll bring down the negative 2. The integral of e to the u is e to the u, and we will evaluate that from 0 to negative 3/2. I'll keep the negative 2 out in front. We begin by plugging in our upper limit of negative 3/2, and then we subtract and plug in our lower limit of 0, and anything raised to the 0 power, including e, is equal to 1.